Hello, this is our concrete mix design report.
By Mazen Mahrouki.
Philip Downs.
Sarah Forsyth.
Emily Lord.
And Nick Cron. The goal of this experiment was to design a concrete mix that was less dense than the traditional concrete while maintaining strength. We did this by replacing coarse aggregate in a normal concrete mix with pieces of glass and bits of rubber. This is important due to the environmental benefit gained by using scrap rubber and recyclable glass. Additionally, it is more cost-effective as more concrete can be transported at once, which reduces the transportation costs. Finally, one of the most important aspects of lightweight concrete is its ability to act as an insulator due to low thermal conductivity. Shown below is the glass mixture after failure. The pieces of glass exposed after breaking are circled.
To help come up with our hypothesis, we did research online about added rubber in glass bits and concrete. From that research, we found that by adding certain percentages of glass, like 0, 5, 10, and 20%, in place of the original aggregate, would decrease the weight of the concrete while not affecting things like the durability. In these articles, we also read that using very small pieces of glass instead of large pieces would increase the compressive strength. And with respect to rubber, we found that using rubber would reduce the density of the concrete, but would not majorly affect the strength of it.
Based on our research from literature and what we learned in class, we hypothesized that adding rubber bits and crushed glass to concrete would reduce its weight with minimal negative impact on the concrete's strength. We thought that by replacing some of the coarse aggregate with rubber or glass, we would decrease the density and weight and only decrease the strength a little bit, so it would still be useful in many applications. We also thought that adding rubber would increase the ductility.
In order to test our hypothesis, we decided to use 3 different samples. One sample without added material, like glass or rubber, one sample with rubber added, and one sample with glass added. Each of the aggregates were roughly the same size as the coarse grain aggregates that we used in the concrete sample. So we removed about 20% of the coarse aggregate's volume and replaced it with glass and rubber. If we look at the concrete mix table here, we can see that the amount of coarse aggregate was removed from each sample for the glass and rubber. However, the weight of rubber added was much lower than glass. This is due to rubber having much smaller specific gravity, which means that it's much lighter than glass. So in order to fill 20% of the same volume in added material, it took about the same weight of glass, but much less weight for rubber. For a visual representation of what this looks like, we can see the mixed diagram shown here for each sample. We can see that the amount of water, cement, and air is identical for all 3 samples, and the same amount of volume was dedicated for rubber and glass in both samples. We can see here that the same volume of rubber and glass has different weights, which is what we saw in the previous table.
After mixing our concrete, we poured the mixtures into 4 by 8 inch cylindrical molds, which we left in a fog room to cure for 7 days. After the samples had finished curing, we weighed each sample and recorded each sample's diameter. These measurements were used to calculate the average density of each of the 3 mixtures. This graph compares the average densities of the 3 kinds of mixtures. We can see that the glass sample had a density that was nearly identical to the control sample's density. On the other hand, the rubber sample's density was nearly half of the control sample's density, which shows how useful rubber could be for lightweight concrete. The first test we performed was a compressive test, where we put 1 of each sample into a machine that pressed downward on the concrete while recording the load, or weight, the sample could withstand. As you can see from the pictures on the right, we had some pretty interesting fractures in our samples. Here's a clip of one of the more exciting fractures that we saw during testing.
Oh my God. That definitely that's a big piece of glass. Look at that. Oh wow. Yeah.
Next, we performed a split tensile test on each sample, where we drew a line across the diameter and length of the cylinders and laid them sideways in the machine shown in the picture on the left. Similar to the compressive test, this machine applied downward force on the sample until it split and recorded the weight the entire time. As you can see in the pictures on the right, the samples were split in half during this test, revealing the components inside of each sample. Enjoy this quick clip of our group breaking the control sample open after its split tensile test.
Oh, look at that. So cool. Oh, I like this because that would look cool. Especially with the glass, yeah. Let's go.
After compiling the data collected from the compressive and tensile tests, we calculated the maximum stress that each sample could withstand during both tests. Stress is a measurement of force per unit area, so samples of different size can be accurately compared. We can see that the glass sample's compressive strength was just a bit lower than the control, whereas the rubber sample was nearly a quarter of the control sample's compressive strength. The tensile test showed a similar pattern. The glass was lower than the control, and the rubber was even lower than the glass. Looking at the rubber sample's average density and compressive strength, we can see that its low density came at the cost of its strength.
The last test done on the samples was the modulus of elasticity test. Modulus of elasticity refers to how much a material changes in length depending on how much stress it is under. Since concrete is very brittle, the usual modulus of elasticity test that runs until the sample breaks is not ideal. So we use a machine called the compressometer frame that we can see in the picture here. This machine can measure the small change in length and diameter that the sample goes through when certain stress is applied. Since the concrete doesn't get completely crushed, the machine goes through 4 total cycles of stressing and de-stressing the concrete. The first cycle is used to calibrate all the measurements and make sure that all the rods are in place. The next 3 cycles calculate the general stress-strain relation for the concrete. We can see in all 3 samples that the first cycle is very distinct from the other 3. For the control sample, the concrete was very stable, and the 3 cycles that can be seen on the left side seem almost identical. For the glass sample, small deviation can be seen in the data of the 3 cycles on the right. And finally, for the rubber sample, measured deviation in the 3 cycles can be observed. This is most likely due to the nature or size of the rubber aggregate that wasn't very compatible with the concrete mix used in this experiment. After analyzing all the data and adding them all in one plot for comparison, we ended up with a graph like the one shown here. We can see the stress-strain curve for the control rubber and glass samples. We can calculate the modulus of elasticity by calculating the slope of the curve of the straight line in each sample. These lines are easily identifiable for the control and glass samples. However, for the rubber sample, the modulus of elasticity was calculating using the average of many calculations in order to have more accurate data due to the nature of the stress-strain curve of the rubber sample. In terms of strength, the control sample definitely had the highest strength, followed by the glass sample close to it, and the rubber sample had the lowest strength. Regarding ductility, which refers to how much a sample can strain after the linear trend ends for the material, the graph shows that both the control and the glass samples had very low ductility, since we didn't see any change in strain after the linear point. For the rubber sample, we can see that it reaches the yield point, which is the end of the linear trend, and it keeps on straining without failure, which indicates that it has more ductility than the other 2 samples.
In conclusion, the glass sample had minimal negative effect on the mechanical properties and density in comparison to the control mix. The rubber mix, however, had a significant decrease in density and mechanical properties. Due to this reduced density and strength, rubber aggregates have potential use in applications that only require low strength but high ductility. The main limitation during the experiment was the availability of resources and time. The number of samples tested was not large enough to make a definitive conclusion about the rubber sample's mechanical properties.
Some future advice for anyone looking to do a similar experiment to ours. We recommend that you use pulverized glass and rubber bits rather than the sizes that we use because they would have much better mechanical properties. Also, we recommend that you test multiple aggregate sizes and a range of glass and rubber concentrations so you can determine which concentration and size of aggregate produces the best results. Lastly, we recommend experimenting with mixing both glass and rubber aggregates into concrete samples to discover how they perform when combined.